A very good evening to everyone who's attending this talk. So I'm Mukund, and I'll be talking on the topic data-driven astronomy. So I am talking as a beginner. So the caption the a beginner's perspective. So data-driven. So let's start with the history of astronomy. So we know that astronomy is also one of the oldest sciences that's existed like so far, and people have since the olden days when the civilizations were like when people started forming civilizations and stuff, people use the bodies use the objects that they viewed in the sky to for their day-to-day aids. So astronomy was a kind of a thing, a kind of a uh, like it was a necessity at once for people, as they didn't have any calendars or like any kind of predictions that any kind of methods to keep track of days. So people had to rely on these astronomical objects to have a track of time and track of months and days, such that they can do like probably like agricultural stuff. They needed to harvest, they needed to plant, and then they needed to like do cattle, and they had agricultural stuff based on a certain specific time. So to keep track of the time, they use these astronomical objects and use the constellations to as their guide in order to plan these events. So and then now that we'll also see have a look at how astronomy was used back in the days. So this is one of the things that was recently found that near the Crace Castle in Aberdeenshire, Scotland, lies a calendar which is over 10,000 years old. The Warren Field is actually a lunar calendar. So it was a lunar calendar that was used to measure time and seasons. It was aligned in a different phases such that the moonlight was, like it falls on that, and they can get to know at what time it regularly falls at each year, and they can get to know at what day and month they are. So it was like a sort of like a lunar. It was like sort of like a calendar or like a year tracker for them. And then there was, as you see below, the Egyptian sundial. So this was a picture sundial which was used to calculate the. It was used to even like have a measure of the time that was that at that point of time. So this was developed in the 1552 or the 1070 BC. So we can see that it goes way back, and people have been developing sort of methods because they didn't have any other reliable sources to have a track of how they are supposed to go in their day-to-day lives. So this is, as you guys also know, like the early models, when people started to invest their thoughts more towards science, when we had made many progressions in the mind. So people have thought to map out the universe based on their observations. So first one, this is the geocentric theory that was modeled by the famous astronomer Ptolemy. So he considered the Earth to be at the center of the solar system, and actually the universe as such, because people have not didn't observe anything other than the solar system back in the days. So he observed the Earth to be at the center of the solar system, and the sun and the moon and the other planets revolve around the Earth. So this was like we now feel that how this this doesn't make sense, and you cannot just like you cannot have a theory based on just your observation and your perspective on things. But at that point of time, it was a groundbreaking theory, and it led to many other theories that was possible because of this. But it only lasted to to a certain amount of time, as does every scientific theory even right now. We see a theory that's been published, like it will be used or it will be verified for a certain amount of time, but then it could also have the risk of being like defamed by a certain another scientist who proves it wrong. So then came Copernicus, who told that no, this is not how the solar system works, and the sun is at the center, and we are just like one among the other planets that revolve other than the sun, and this is the heliocentric theory that was devised by Copernicus. And then now we've had a general overlook out as to how astronomy was used and how astronomy was practiced back in the days. So now let's have a time skip and look at what we're doing right now. So as you all guys know, this is a Hubble telescope. So the Hubble telescope is, revolving around the Earth, and it tracks all the ultraviolet and infrared radiations from various galaxies and various distant sources, and it sends us the data. So see from where we've gone from observing the moon, the sky, and the stars within our solar system, and we've extended our range to other galaxies and other solar systems. So such is the scientific discovery. So science, it's just a rigorous process where you get to, like there is nothing like a backward evolution of science. There's only like the going forward in science. So then, yeah, we've also introduced the topic, the concept of spectrometry, wherein we observe what are the emissions that are being absorbed by the certain bodies or certain stars, and then we try to figure out what are the kinds of elements and all the kinds of gases that are present in the star. So in this case, we can see that the star absorbs the black lines that are present in this scale shows the absorption spectrum. So a star or any body as such will absorb some certain radiations and then will emit certain radiations. So the absorption radiation will not be the same as the emitted radiation. So these stars the star in this case absorbs the radiation at the ultraviolet range and some of the infrared range, and then it emits at the rest of the range here. So with this, we can also get to know what are the kinds of elements that are present and what is the nature of the star. So think about the scientific development that has been, going on for the past couple of centuries right here. And so here is the most famous Hertzsprung-Russell diagram. So I guess like people in second year would have come across this thing, but here this is a way that is used to classify the stars based on their luminosity and their surface temperature. Luminosity, in this case, we are observing the magnitudes of the star with respect to our sun, apparent magnitudes. So we see this main sequence here, the diagonal from the top left upper left corner to the bottom right corner. So this diagonal it's basically like the most common stars in the universe. So our sun also comes in this range, and the upper left corner is occupied by the very high energy stars, and the bottom right corner consists of like low energy stars and smaller stars. And we see in this case the luminosity of the white dwarfs, in this case the below ones, and then on the top we see the supergiants. So this gives us a general outlook of how we could classify the stars based on luminosity, that is their brightness, that's flux. So flux density is nothing but how much radiation is being received by a body per meter square. So basically, we measure this in form of Genskis. One Genski is like 10 to the power 10 to the power 16 radiation per square meter per hertz. So we usually measure the flux density in this form, and then we could classify the stars based on this. So this is the general classification of the stars that we even use till today. So the O star right here is like the very high energy stars and very large stars, which gives out a lot of radiation per square, which has high luminosity index and gives out a lot of radiations per second per meter square. And then it goes all the way till M, which is the cool set of stars which are like small and then doesn't emit a lot of radiation per meter square. So this was a naive it was a naive classification of stars that was done using only two factors, that is the luminosity and then the temperature. But we cannot devise the distance between each of the stars from this case. So that is one of the drawbacks in this. Now let's head over to our main discussion of today. Introduction to data-driven astronomy. So science is, as you guys know, is going under a data explosion, and astronomy is leading the way. Modern telescopes produce terabytes, even petabytes of data per observation, and even simulations require to model our observable universe to push supercomputers to their limits. To analyze this, we need to be able to think computationally to solve our problems. In this, through this talk, we'll investigate the challenges to working with large data sets and how to implement algorithms to work and how to use the databases to manage the data and how to learn from the data with machine learning tools. So this is the general outlook of what we will be learning from in this talk. So the first module of this is stacking. So why do so why do we need stack? What is stacking? Stacking is nothing but a statistical approach to derive the input signal better by excluding the surrounding noise in the observational data sets. So you guys know that while observing like a body, so the observations, the input observational data sets which you get are not consistent. You yeah, in such a way that your input signals are like overcrowded with the noise that is being observed along with it. So say you're observing a very distant star. So you're using a radioscopic observational technique here. So there are many other objects that are surrounding it and that also emit radio wave emissions. So when we get the input signal, we also get the noise along with it, and due to the noise, we cannot make like efficient conclusions with it, and so we needed a better method to do so. So stacking is one of the methods that is being used here. So in stacking, we locate the points of the pulsar signals. So in this case, we are looking at a pulsar in this case, as you can see here. So this is an example of how a radioscopic observation is done. So here we can see the black dots in this mapping scale, and then the black dots are nothing but the observed pulsar radiations. And then the surrounding gray color we can see here are nothing but the noise. So one second. Yeah, just can give you a better idea. This is a distant radio galaxy here, the black dots, and then the surrounding gray is the noise. And these here are the supernovae remnants, which linger on for a lot of years as the radiations are very high and very powerful and stuff. So this is how a radioscopic observation is done about. And then what we do is we locate the points at the pulsars of the pulsars where the signals are detected. And what we do here is, in this case, we see the signal of like the input signal of the pulsar is in the center of this thing. And then the next module, we can see that the signal is missing here. We're not able to detect a signal here. So this could be due to various reasons, such as like the emission of the radiation is not spontaneous, or another body has absorbed some amount of radiation, which has led for a not inefficient signal that is being mapped by the telescope. So what we do here, we need what we do here is we take multiple images at different instances. So we take now here around 12 images, and then what we do is we try to stack them. So by stacking, what we actually mean is that we take them we take the points that are in the center. We take the points that gives us a detection that the pulsars are there, and we try to shift the images. We try to shift the input signals to the center of the image. So while we shift to the center of the image, what we do is we try to take the mean of that. When we try to take the mean of that along with the noise, what happens is you guys must have come across constructive interference and destructive interference. So the top left graph shows us the input, the detection. So we can see the amplitude of that is of a unity. We can see a detection there, but to the to this graph, we can see the noise that is being present along with it. So to like get our information about this thing, so what we do here is we try to merge the input signal along with the noise, and then we do the mean stacking. Sorry, we do the mean stacking. Mean stacking is what we've seen. Like we try to move the detection of the pulsar into the center of the image, and we try to find the mean of the detections. So in this case, what we can do is we try to take the mean along with the noise. So the noise itself forms the graph of the image that is being detected. So from this noise, we can find an underlying signal that is being present. So this is one way we can use to get an efficient and a sufficient data from the observed objects. So this is like a flow chart as to how stacking is being done. First, find images containing the position of the known pulsars. Crop and shift each pulsar to the center of each image. Then find the mean brightness at each pixel of the image. And then we get a new image, which is the total, like a clear input image of the pulsar that is being observed. So this is how stacking is done, and we move to the next one. So one might ask one. So after like practicing mean stacking, also we have found the datas were not were not that accurate enough using it. So what we did is we tried to use a median stacking. A median stacking is nothing but the same process. You try to shift the image to the center of the pixel and try to calculate the median of the image rather than the mean of the image. So why is median better than mean? So in this case, we are considering a uniform data. That is, we are observing only one pulsar at a time. So, but what if we detect like a non-homogeneous information? That is that the homogeneous information is such a way that homogeneous data is such a way that the mean and the median lie at the same point. But what if we try to do it for a non-homogeneous data set? So in this case, we can see that the mean is shifted towards the right, but the median is towards the actual result of the data. So we thought of this, and then we come across a solution that the median was much more robust and efficient compared to the mean. So we in this case we use the median instead of the mean for the stacking process. So uh, as you guys have seen that we had like 12 data set images in order to just do just a simple stacking, but that's not all about it. So when we try to observe more and more distant galaxies, we have more and more noise, so we need more and more image samples to perform median stacking. So with all of these data sets combined, we need a perfect we need to store all the data sets at one time, and we need to perform the median. So, but then if you do it with a normal layman's algorithm, there, it would take you more than 2,500 minutes to calculate just the median of the stack. So it is obviously not efficient for us. So 2,500 seconds. So it is not efficient for us, and it is also not a good program to let our computer run it. So one solution to this is that we change our algorithm. So one such solution to the memory management of the dataset is the bin-approx algorithm. So the bin-approx algorithm works in such a way that there is an image. We detect a input signal from a pulsar. So what we do is that each pixel you try to put it in a bin. We try to put each pixel in a bin, and then we try to generate a histogram of each pixels in the bin. And then we try to like the sum of each pixel in the form of a histogram. So when we reach at exactly the midpoint, that is the say like you fit it into 10 bins, and then if you try to if 10 bins and you have 20 inputs, so when you reach the fifth bin and the sorry 10th fifth bin and the 10th input, you try to calculate the mean at that bin itself rather than doing it over the whole data set. So in this case, we are increasing our efficiency by 50% by reducing our workload. So let's take up to this. Let's take up to like say 10,000 data sets. So we try to put it in a histogram way, and then we try to calculate the mean from of each data set in a in the bin, and then we try to reach at zero. At zero, we can find the value of the median instead of calculating for the whole range of data sets. So this is how bin approximation algorithm works. So let's understand this better with an example. So we have n number of bins of unit capacity. and we have the given data sets that is like zero point 0.5, 0.7, 0.5, 0.2, 0.4, 0.2, 0.5, 0.1, and zero point 0.6. So we need to these are what the pixel data actually is. It's an example of a pixel data which we need to fit in the bins such a way that you can maximum space in a bin by reducing the number of bins being used, and then reducing the like fitting it up to the maximum capacity of a bin. So we come up with an optimal solution as such. So this is how you would try to pack the data sets efficiently by leaving very minimal gaps in very minimal like leftover space in each bin, and occupying the least number of bins that is required. So this is how approximation algorithm works here, and then we can just calculate the mean/median from here. And see, this is the image we get after performing the median stack algorithm. We can get a clear detection of a pulsar by reducing the surrounding noise in this. So this is all about the stacking process here. And then cross matching. Cross matching is nothing but to find the cross matching is a process to like relate two data sets that complement each other, like that are that are complement each other. So we see galaxy A in this detection, and then we detect the galaxy B there. So we need to find, say, the distance between the two galaxies, or to understand what kind of galaxies are they. We use the cross matching algorithm. So in this graph, we see this is the galaxy, and this is the galaxy B. So here we see galaxy A, but then here we see here is a galaxy B. So how do we actually calculate the distance between the two galaxies? In the first catalog, we see a detection in the galaxy A that shows the local coordinates 12, 34, and 56. These are the coordinates. And in the catalog 2, we see a 3 detection candidates. But then what we do here is with the given program. So for source A in catalog 1, and then for source B in catalog 2, we try to calculate the offset. Offset is nothing but the distance between the galaxies. That is the like devise a function that the angular distance between A and B. So then we can like find the value of A and B, find the distance between A and B. So if the offset is less than the radius of our scaling factor, so say the radius of the scaling factor is nothing but how to what extent you want your search radius to be here. You see the circle here represents the radius factor in the imaging scale. So if the given galaxy is within the radius factor, the best match, that is the given distance between two galaxies, is the best match and the best result that you can get from the image. So this is how the cross matching data works. So now let's go on to machine learning. Machine learning, obviously, as during the talk we've talked about, is like you train the machine by repeatedly feeding it the inputs that you want to, and then you train the machine to do it with an unknown data. That is the ultimate the goal of a machine learning. So in the given course, we use machine learning concept, and then in this we use one catalog called as decision tree classification. So say I need to train a bot to tell me whether it is favorable to play tennis today. I give it, so the factors that I need to work on is the general weather outlook, and the temperature, humidity, and the wind. These are like the 4 basic conditions that we need to check before the tennis match is held. So I give it such a data such that I give it such inputs for a certain number of days. So it's day 1, it's sunny and hot, and the humidity is high, and the wind is weak. So, but since it's sunny and hot and humidity is really high, it gets really tough for the players to play over a long period of time. So it is not favorable to play tennis on that particular day. So if it is sunny and hot and high, and the wind is also strong, it is not favorable to play. So if the weather is overcast and it's hot and it's high, so overcast weather, it's playable under those days. So we give it to train such modules give it to train such module of the given data such that it can use these data to form its own decision tree algorithm. It can form its own algorithm and can learn and kind of give you the output as to when can we play tennis given the conditions. So in this case, it forms, we write a program to form a decision tree. So the main field is the weather. So there are three kinds: sunny, overcast, and rain. So coming to the overcast section, we can notice that whenever the outlook is overcast, it is always favorable to play tennis in those days. So what it does is, it as soon as it detects overcast, it just gives you the result that we can play tennis. But when we go over to sunny and the humidity is high, we always see that we cannot play tennis. So if when it's sunny and the humidity is high, it shows we can't play the tennis. We can't play tennis. But then when the sun, when it is sunny and the humidity is like, weak, or I mean, sorry, normal, we always see that we get the output of yes, we can play tennis that day. So it forms a section that when it detects the weather to be sunny and humidity to be normal, we can tennis can be played on that specific day. Now let's head over to the rain section. So when it is rainy, when it is rainy and the wind is weak, so in this case we've given the data that yes, we can play tennis on that day. But when it's rainy and wind is strong, we can see that we cannot play data on that specific day. So it tries to form a tree branch such that from when it's raining and the wind is strong, we cannot play. When it is raining and the wind is weak, we can play. So by training the machine using an algorithm, by giving it in certain set of input, the machine learns from the given algorithm, and it can predict what will happen on that specific day given the specific parameters. So this is how decision tree classifiers works. So now let's use the classification using regression. So regression is a statistical concept as where you give in numerical outputs. You give numerical inputs and then it gives a numerical output for you. You train the machine by giving it numerical inputs and then it gives you a numerical output of a untrained data. So that's how regression works. And now let's have a look at an example in this. So we see this is emission, this is an flux emission spectrum that is being done for a star Vega, which is I guess like 10,000. Its temperature is around 10,000 kelvins, and it is like 25 25 million light 25 10 million light years or something. Yeah, 10 light years. Yeah, so we record the luminosity of this using this graph. So you have this U, G, R, I, Z are the different filters at different wavelengths to measure the spectrum coming from this, measure the radiation coming from that star. So what if the star was moved further apart, say another 2 to 3 light years, 2 to 3, like it's moved far. So what we observe is the redshift, obviously, because as the objects move away from each other, that is with respect to us, that wavelength tends to increase. So we can detect a redshift there. So we see that the wavelength under the 600 range will move to 0.4 towards the towards the right. It gets redshifted at that range. So Z is a measure of the redshift that is being done. So how do we calculate redshift for an unknown galaxy? So we know we're able to plot the graph, and we're able to calculate the redshift manually by using our own algorithms, human algorithms. But we need the machine to do this. So what we do here is that we decide and we try to train the machine with repeated data sets, and then we try to use it on an unknown galaxy for which the radiation, like the graph has not been planted on the radiation has not been captured. So we let the machine to do that, so that we don't have to do it manually and don't have to go through the tedious process again. So what is the main factor that is required to understand the redshift? Obviously, we do it using color indices. So these are the filters that we use: U, G, R, I, and Z. And the color factor, or the color, is nothing but the individual difference between the two consecutive filters. So the color U minus G and then G minus R and R minus I and I minus Z are the different colors that are being observed at different wavelengths. So what we do is here, what we do, so in this case, the two graphs are not the similar for the same galaxy. Why? We can see that this could be of two reasons: that we've not received the correct input in data inputs, and second one, this could be due to the unknown redshifts that has happened to the galaxy. So what we do, we want to calculate the redshift of the galaxy. So what we do is we give it multiple input samples. We train it using multiple data. So we give it tests and then targets to give us the result. So we give input all the datas in this, and then what it does is it forms a decision tree of itself. So decision tree, first we can see the column that u minus g, when it's less than or equal to 0.7475, it goes to two sections, that is true and false. The value we get here is 0.296, that is the redshift value using the algorithm. So when the difference between the difference between U and G filter, that is the UG color, is less than 0.7475, there are two possibilities here. When it is true, it goes to G minus R, the second filter. But then when if it's false, it goes to R minus I, the third filter. So what happens here, if the third, again, it tries to go with the given data, it tries to compute the value of redshift for the G minus R, the GR spectrum. So then it goes, if the value of the GR spectrum is 0.372, and then it gives you two output optionality, that is the next one in the queue, I minus Z and then R minus I. And then if it is false, it goes to R minus I, and then if it's less than 0.0825, it goes to I minus Z and then G minus R. So what we're doing here is basically we are trying to give it a certain conditions to where the redshift can be found for a given set of data using the we train it using the given input values. Say if the 0.7475 is an input value of a calculated redshift in the UG range, and then if it is true, it goes to the GR range where it is 0.372 is the calculated redshift, and then we find the value of it. So here it calculates the optimal least value, and then here is the optimal solution for us. Here, so the what happens if it fails at this stage itself? What if the condition of 0.7475 is not met? We find the mean square error value. That is when if the condition is not met, we get the mean square error value as a result. So given the, like, this is how the decision tree classifiers are used to with regression to calculate the redshift of the given galaxies. Yeah, and then this is a decision tree regression graph. So the diagonal, the dark line you can see here are the correct ones, like the correct redshift that is being computed by the computer. So but then we can also see that the computers has like given bizarre results at points where it is marked with a circle. So we can see that it is always a hit or miss with this. But with by continuously feeding it enough data, we can train the machine to learn and to give us the input for an unknown galaxy. So one of the drawbacks of the decision tree algorithm is the confusion matrix. Confusion matrix is a measure of how well your data, or how well your program is being performed, or how well the machine is interpreting your data. So in the diagonals, the 85, 117, and 98, these are the numbers that indicate that these many times the computer has done it correctly. These many times your algorithm was was performing correctly. But then we also see this here, the 13 times, 29 times, 3 times, and 13 times, and 32 times, it has performed incorrectly. So that is the given data, and to check how well your algorithm is and how well your program is and how well the computer is interpreting the program. So the confusion matrix works in this way. This is the measure of how well your program is working. Now let's go to the ensemble classification. There are the data can be interpreted in machine learning via two ways, that is regression and the other is classification. Regression is nothing but you give individual integer inputs to your data, and you get a continuous integer input for your output for your data. But in classification, you don't get you give a condition, and then it returns back a condition involving the data. say for example, I need to pay, how much do I need to pay to buy to sell this house, how much do I need to sell the house for. Regression says that if you sell it within this range or this range, you'll have this much profit. If you sell it within this range and this range, you'll have this much loss. But then what happens is, classification says that if you sell it at this point and this, if you sell it within, uh, uh, if you sell it to this person and this person, considering they're able to pay this much and this much, it will be a loss for you or it will be a profit for you. So that's how regression and classification like works. So in this case, and one more difference between regression and classification is that for regression you use the same data sets, like the same inputs, and the, like same format of inputs, that you need to calculate the redshift, you need to calculate the brightness. Those are the same value inputs that you give to regress, to make the computer learn from it and then give you for a unknown galaxy. But then during classification, you train it with different parameters, say the brightness, the radius, the luminosity and stuff. So with that, it collects all the collective data into it collects all the collective separate test samples of different parameters and then tries to combine the parameters into one and give you an output. So the output here is in the form of whether or not the redshift exists or not, rather than giving a value of a redshift. But then regression gives you a value of a redshift. It says 0 or some plus 0.72 something. But then in classification, it just tells you that whether there is a redshift that is being spotted there or not in the specific galaxy. So there, by using the ensemble classification rather than the regression, we can see that the computer has predicted more, predicted correctly more number of times rather than that. So we see here 95, 121, 108 times it has predicted correctly, and there is only like very little times when it has predicted wrong. Now let's go to how galaxies are classified. So there are three types of galaxies essentially. One is the spiral galaxy to the left, and then in the middle is the elliptical galaxy, and then to the right is the irregular galaxy. The spiral galaxies have you can see the spiral galaxies. You can see the like a sort of a line that is there from the nucleus to the first arm. So this region is called as the bar of a spiral galaxy. So, but in the elliptical galaxy, you don't have such a thing as bar, and irregular galaxy you don't. So, based on based on the features of the galaxy, we can Edmund Hubble had classified them into various parts using the Edward-Hubble tuning fork system. So here to the left, in here we can see all the elliptical galaxies, and then on the top here we can see the spiral galaxies, and then we here spiral barred galaxies, and then here we can see the irregular galaxies. So the S0 and the SB0 are the galaxies that are in that whose shape is like neither a elliptical galaxy nor a spiral galaxy. So the E0 here indicates that the galaxy is almost circular in shape, and it has like no bar in between. And then as to go on and to E6 and E7, that means it is the elongation is very much noticeable, and it is like most elliptical compared to the other galaxies. But in the spiral, we see here SA, SB, SA, and SC. In SA, the bar length is not that noticeable, and then bar length is not that noticeable. But then if you go towards the right, you can notice that the bar length is quite visible, and and it has many arms around it, more spiral compared to this. For the irregular galaxies are formed when two galaxies merge together. So when they merge together, they don't form with a specific shape, and they don't come under the elliptical or the spiral galaxies. So they come under the forms of irregular galaxies. So now to the final module of the this thing is sociology in astronomy, data-driven astronomy. So so by sociology we mean how different fields and different communities can like come together and help science improve. So we see in data-driven astronomy, we see there are three fields that are being involved. We see that machine learning, that is computational aspects, is involved. We see astronomy involved, and we see statistics involved. So these three fields combine to form a separate field, which helps us to like determine various aspects of the universe that was not otherwise not possible with the existing methods that we had. So in this, by this way, we can all, like Carl Sagan's as an example, his mentors both, one was a microbiologist and one was an astronomer. So they both were, like they, due to their ego issues, he was thinking both were wrong. But Carl Sagan, he thought, what if I could, like unite them, unite their theories, and then I can open up a new field which handle both. So Carl Sagan was successful in that. He got mentored by both of them, and he united their two theories, and then he came up. His theories were more successful. So in this way, we can also like unite together. We can improve our learning by merging many fields together into one, and then we can learn more about the universe than we already do. So I would like to end this by saying the quote that it's not that there are things that science can't explain. You look for the rules behind those things. Science is just a name for the steady pain in the ass effort that goes behind it. And thank you guys. The talk is